Okay, so as you remember, last time we have taken a look on how classes work, which is the most important feature of C++. It is what enables us to do all the typical object-oriented programming. And at this opportunity, we also have taken a look to explicitly look into how this constructor and destructor mechanisms work, which have allowed us to automatically, for example, clean up resources once a variable goes out of scope, which is located on the stack. And today, since we already had many things during the last lecture, we can skip directly to templates, which is a function of C++ that allows C++ to behave to a certain extent like a type agnostic language, which can be extremely useful. Generally, using a truly type agnostic language is, while convenient, at the same time quite risky, because it's easy to do mistakes which will only be detected during runtime. So this is not something that you would want to use for security critical applications, or maybe even at all. Just to have said it, such type agnostic languages would be, for example, PHP or JavaScript. And especially in the case of JavaScript, from the sheer fact that people have invented TypeScript, it is quite obvious that typing and strong typing is something that is very important if you are developing a larger program. But at the same time, obviously, typing might be inconvenient. So in C++ we have the concept of a template, for which we'll start a new project now, which allows us to write a generic code snippet which then the compiler can specialize to whichever particular fixed hard-typed type we want to use it with. So we create a new project, we call it templates, create, and we will start with the simplest type of a template, just a function template. So as you remember, a normal function is written like, let's say, int make average, make avg, and then we provide to it a int values just as a pointer, and maybe value count, so that we know how many values. Use type t for count. Okay, so we start with a very normal non-template function, and then we will specialize it to it. Then we will not specialize. Then we will generalize it to a template. So in the normal case, we would have like a int result, which would start as 0, and as the final result, we would return result divided by count. And since we cannot divide by 0, we could have here a safeguard. If count is equals 0, then we just return 0. And in between, of course, we would have a loop for int size t is equals 0, is less than 0 is a typo, 0, null, and I++. And the body of the function is likewise very trivial. Result is just plus equals values from I, and that's the whole function. So as you see, we have a very simple function, and now we can use it if we want. So let's create an array, int e values, let's say it's an arbitrary size array, and then we put a few values into it. Int e this from e values, comma, we need to include some helper. Let us include Windows H, that should already contain array size I. So that would be our simple, trivial, non-template use case. We can run it just to see that it does something, and then we see, of course, that we get a result. Apparently it's 4. Obviously, since it's it might be 4 point something, but we're using integers, so we don't get any commas. So maybe we would want to change it. So let's say we would want to have floats, or better even doubles. But then of course if we would try to do a thing like this, the thing will complain here that we cannot handle that particular type. And one very labor-intensive solution would of course be to just copy the whole function, change the type to something else. This is another feature in C++ which is quite useful, that you can have functions with the same name, just different types, and then C++ automatically, the compiler automatically picks the right type for you. So here in this case we just created just a full duplicate of our function, and then now of course we need to call it also D result. Then we can run it and we will get a result which is in this case the result. Well, it's still false, so apparently there are no commas, but we could like use 1.1 and 2.2 just to change it, just to mix it up a bit. So wait, still that doesn't do what I wanted to do. We have double, we have here double, so probably here it is casting to int because we're dividing for an integer, so we can just cast it to double to be on the safe side. And now when we run it, it should give us some no, the bug was a different one. I forgot to change the type here, so here it casted us down to an integer. Right, so our real result for this is 4.9, and if we switch this back to the original value, we probably also get a fractional result. Zack. Well, 4.5, that's pretty much what I would expect. So as you see, it works, but as you see, it is very labor intensive. If you would have like a few more different types, like you want one for char and one for short, and then maybe for signed and unsigned, then you are probably getting to and then for float and double, then you probably will end up with 10 different copies of the same function, which obviously is very inefficient. So what we can do is instead we can use templates. We just write template type name t. We could use multiple types, so we can write comma type 2 and so on, but for now we just start one, and then we just replace the int in our function with this placeholder. So t, type name is a keyword, t is the placeholder. We can use like my type instead. Maybe I should use my type. That sounds more, that makes it more obvious that this is something we can change at any point. And now as you see, the functions here, they are fine, so they are no longer complaining that one of those types would not work. And now when we put a breakpoint here and here, we can see that while we only have one function in our source code, effectively the compiler will copy it and make a new instance of it for every type it sees us using. So here we are, and we see that our make type int has this offset, so this address, and when we look here we see that the other, so the name, the internal name which is generated replaces the type name with our type. So the function internally is called make average pointy brackets int pointy brackets, while the other implementation for double is called make average pointy brackets double pointy brackets. And if we step into it, we really see that once we are past the jump table, that we end up in a implementation made specially for this. We can jump out and then go to the other one and then jump in here. Okay, jump table. Then we see again that here different operations are used, since here we are operating with doubles. It still shows us the same source code, which helps us with understanding what this template is doing. But on a physical level speaking, the address of the function is different, and it's just another implementation of the same thing. I guess if we would be scrolling enough up and down, we would find the other implementation if we would want to. And now of course we can just add any other type we would want to add, as long as it's supported. So let's say let's define a type uint64, so we can now use an uint64 here, but let's call this then u, or we could also call it L for long and here as well. And as you see, it works just fine. It gives us here again an integer result. And the important thing is that if we put a breakpoint here, we see then again we got yet another instance of the function. In this case, make average uint unsigned 64. So as many types as we want to use, as many instances of this will be created. And the way this works is that this is not restricted to only machine types. So we could create here, let's do another example. Let's create a structure, my struct A, oops, and another structure, my struct B, and let's give it values int var A and var B and var C and var C, and here we will, let's give it variables var C and D and F, D and E. So we have one variable name which is shared amongst them, but it's in a completely different position, and it has, and all the other content is different. Or maybe to make it even more different, we even change one more so that we have different sizes, such that the structures are really highly incompatible with each other, binary wise speaking. So, and now let's say we want to make a function which template T1, T2, oops, and let's see what we want. Let's say it returns T1, my struct add, comma T1 var1, comma const T2 reference var2, sorry, type name. That's small oversight. Return var1 plus var2 dot, and then it doesn't suggest us anything because it doesn't know what T2 might be. But we, for example, let's say we will take var C. So now here we will create my struct A and B. My struct A is equals 1 1 1 2 2 2 3 3 3, and my struct B is equals 0x AAA 0x BBB, and that's all because we don't have more room. And maybe I will add here 0x as well so that we see in hex the same thing. Okay, and now let's say we want a int as return, so int ret1 is equals my struct add 0x f123, oops, comma, and then we just pass it one struct, then we use the same function with the other struct, and as you see, the compiler is not complaining because it creates two independent implementations of the function, one for struct A, the other one for struct B, and the only thing that really is a requirement is that the variable name which we have here for our complex type still exists. It doesn't care about anything else. So if we run it, again we see that there are different should be what we'll call should be different addresses. Oh, of course, it's the same address because I didn't change this to struct B. I was puzzled there for a second. Now we see that there are different addresses where the different functions live, and we don't need to step through it. We just run the code. We can put a breakpoint here. Then, as we see here, it shows us we can inspect the variables. For the other one, we already have seen it. Let's run it again so that we see it fully. Don't need those breakpoints. So for one case, we see here the ABC, and for the other one, we see. So the compiler, the debugger knows in which instance we are and shows us the right IntelliSense information for whatever structure we are using right now. And obviously here, when we continue running, we'll see that our result, just let's enable hex, is what we expected. So it performed the addition as it should, and that's that. So this is more or less the extent that you can use templates with functions. And of course the next level of using templates will be to use templates with structures. So we can, again, we start with template team, and then we copy one of our structures. Let's call it structure C. And now we could use, instead of a type here, our placeholder. So let's extend our example. Struct C. Struct C, and now as you see here, the thing is complaining slightly because it doesn't know how struct C should look, because while here it could deduce it from the arguments we have passed to it. It just looked on it. Okay, this type. Can I make a template for it? Yes, I can. So let's do it. While here for the structure, it does not. It cannot deduce it easily from the past arguments. So what we need to do is we need to use the pointy brackets and explicitly say that in this case, let's say we want our uint64. Actually, I will define this at the top. That's more appropriate. Of course, as whatever works, but there are good practices to make readable code. So as soon as for our template type, we provide our type that we actually want to be used, then it was able to create the template type, and then we can of course use ret3. Right, this was a bug that should have been double. We don't have much warnings enabled, so some castings where we might lose data is just done without asking. But in this case, now we have fixed that. So when we run it again, we see that it is operating as expected. And now we have a template function and a template object. And of course we can combine this. We can create an object. Let's think what would be a good example. We can, for example, create a smart pointer, which would then combine the features of having a template type with a template object. So again, we start. We'll call this ptr. We'll call it my. How do I call it? I will call it a handle, because we'll later extend it to be more flexible, and we should use class, maybe. Doesn't matter much. Just it's customary to rather use classes. So we'd have a handle which would take type ptr, which already is a pointer. So let's say it takes const pointer ptr. Then we need a destructor. Then we need some protected data of type ptr, ptr, and here we can now. So everything that we have as a template at the top can be used within the whole object, and also in functions and as types outside. So this works fine. And now what we want this class to do is we want it to just delete whatever we have passed to it as a pointer once we are done. So this is like the most trivial example we can have of it. So let's create here a scope. My handle from new int. Let's say it's an array with 10 entries. In this case, it wants us to specify which type we want it to handle. But if we would switch to I think C17, then it would be smart enough to actually deduce it from how we initialize the objects. Let's quickly check that. C7. Let's go with C20 directly. As you see, with the newer versions of C++, you need to be less explicit with what you are writing. But since a lot of things still uses, which one was the old one? Default. Yeah. Let's go with the default. The C13. Then let's do it still manually and specify the type. And now when we put a breakpoint here and there, we will see that the thing gets created, and then when here we go out of scope, the destructor is automatically called. So if we jump here, we see that from this closing brackets, we are coming to this destructor, which then deletes our memory, such that we don't end up with a memory leak. As you might remember from our lecture about memory management, freeing allocated memory is very important, otherwise your application will crash at some point because it won't be able to allocate any more memory. Obviously, such a extremely simple class is yet not so very useful. So what we can do is we can specify a few operators that will help us doing things with this class. So one could be, for example, the error operator. So ptr is already the pointer. Actually, we should change this to make it to allow us for more types. So we'll go with just t, not pointer, and then we will change this to t asterisk. That will be more flexible. T asterisk operator error suck return ptr. Then we can have a t reference of type reference, which pretty much does this more or less the same. We just need an asterisk here, and then we can also create an operator. So t reference square bracket operator index, which will return a value at a given index. And we could also define other operators of type const. So in principle we could that's not how we write it, that's how we write it. So we could in principle copy all of them just to have a const version as well. Which usually is useful to have. And now we have here our array. We could have a handle, a loop for int e is equals null, e is less than 10, e plus plus, and another one. In the first one we can fill this thing from I is equals I, and here we will, let's say we want to print this. So printf, we need some include to use printf. stdio printf %d \n comma from e. You can run it, and then we will okay, it's comparing with something. Right, it doesn't like converting const to non-const. We can just force cast that, then it will be fine. And as you can see, it did what it should. It printed the numbers before it filled them out, and then here, if I wouldn't have pressed stop, it would have deallocated the memory automatically. So what we have here is already a so-called smart pointer, because it behaves like a pointer, but it is smart in that sense that it manages the memory for you. It is an extremely primitive version of a smart pointer because it does not handle assignments. So you cannot assign this smart pointer to another instance of this type, and then have it reference count the references and then do memory freeing only once all the references went out of scope. That would require a bit more code. and also some larger memory usage. So we might look into it a bit later, but for now, for the simple use case, this is good enough. However, it has a certain limitation, which you might have noticed. We have used here the new int square bracket operator, which is creating an array. But for deleting, we are just using normal delete, while officially we should use this operator here. And the problem in this particular case is that we don't know here which in which way the memory was allocated. We could have written here malloc Caesar of int types 10 int asterisk. So our smart pointer, while being smart, is not yet reliable, so we would want to improve it by making it a bit more complicated. We'll add another type. In this case, I opted, instead of calling it T1 and T2, to just call it T and U, but we could also call it whatever we want, like D. And now the idea is that our type D will be a deleter. So here, this will be a function pointer, which we'll use to delete whatever we pass to it. Of course, now we need to set this variable as well, so we'll add here another d asterisk, not just d, deleter ptr, oops, not ptr, just deleter equals deleter. We could, or we call it just del. It's faster to type. Del, yeah, I like this more. Suck. And now we somehow need to pass a function to it. Plus, what we also need to do is to specify here a type for this. So maybe for simplicity, we really switch now to the newer version, so that we need to type less. And now we can here provide a delete function, for example, in the case of in the form of a lambda function, asterisk ptr. Oops. Delete. We can break this up into multiple lines so that we can put better breakpoints. Let's put a breakpoint here, a breakpoint there, and okay. And now, when we arrive at the end of our scope, when we continue running it, we end up, of course, here. But this time, delete is our custom delete is invoked, which we have defined here. And then the right type of delete is used. So I call this variable my handle because we could use now this type of object to automatically release any sort of handles which you might encounter. So for example, on Windows, when you want to access a file, you would use file open to create the handle, and then once you are done with reading or writing from that file, you would use close handle or anti-close to close the reference. And like with allocated memory, handles also need to be freed, otherwise at some point your program or the entire system will run out of resources and you won't be able to create new handles, which would be very bad, because probably then the whole operating system would crash. Obviously the total handle limit is like, I actually don't remember what the total limit is, but there are some limits in the order of a few 100,000 handles, I think. For graphical objects, the limits are much lower, with just a few thousand objects, but for handles this is large, and also it was like increased from one build of the operating system to another. So if you can easily handle 65,000 handles on Windows 10, with Windows XP that would probably be enough to crash the whole system. So it's not a value that you can remember, no, okay, then it will always be fine. This changes with time. You just should generally minimize the amount of open handles that you are holding if you don't need them. And now, of course, here instead of delete, we could also use this close handle or anti-close or whichever other cleanup function we might need to get rid of our particular type of handle or resource variable. And of course, once we are done with this then at some point goes out and goes back to our done function. So that's that. You might of course find yourself in a situation, so let's now go back to templates in general. You might as I mentioned, find yourself in a situation where you might not be able to write a template that would cover all your cases. As we see here, in this case we need to know the var_c, what var_c, so we need to have this var_c member on our var2, but we maybe want to use a completely different structure. So let's create a structure, how do we call it? This was C. Right, so let's call it structure D. I will move this further down so that we have all the structure definitions in one place, and then our other definitions. So we have our structure D, and our structure D is characterized by not having a var_c variable. So if we now try our trick of our structure, actually we can do it here. Of our structure D, let's initialize it again with something, and of course the name here needs to be changed as well, otherwise it will not work. Our structure D had int as type, so let's go back to here to use int. This will be type 4 and structure D. At this point, as you see, it's not even complaining because the IntelliSense is not complex enough to actually try to implement your template function instantly. But if we try to compile it, it will throw an error and point us that the type conversion here is not possible. Variable C is not a member of struct D. So it says what we expected it to say. It cannot handle the case. So how do we handle it if we would want to somehow be able to handle the case? And well, what we can do is we can copy our function and then manually implement one special case. So in this case here, this is struct D, and struct D takes D variable instead. So here the template kind of breaks down. We need to manually make a copy, but this is already enough. And then when we run it, okay, I didn't put the breakpoint where I should. Let's put the breakpoint quickly here. So when we run it again, we see that now here it is using our explicit copy instead of a implemented version. So this way you can easily make specifications. Another use case, for example, would be if you would go back to our average function here, if instead of a array of numbers you would want to pass to it an array of strings which contains numbers as text, then also this of course would break down and would not be able to handle it. But instead what it could do is it could what we could do is we could implement a special case that then would allow us to pass to it a variable which contains strings. So that sounds like a good exercise. So let's write this down as a homework. Char, do we need the char asterisk c values arbitrary length is equals 1, does this work? No, this doesn't work this way. Wait, that is a bit annoying. We would need to predefine the variables here. Alright, we can. Actually, it should work. We probably just didn't like this not to be const. What? Yeah. Okay. 2, comma. That's boring. Oops. Okay, right, yo. So let's see result. Array size. That should kind of work, of course. And this of and we of course want, let's say, want an integer as a return value. So we will comment this out. (16.05.2024) a make array. Average. And if you want to convert a character, what you can do is int let's say value, say for 3 what's see no, toy not just atoy, sorry. Toy is for white cat, atoy is for this. Let's say we wanted the number 3. And voila. So basically you can just pick individual const char pointers from your C values inside the function here, kind of like this. But then you need to use the atoy function to convert it to the integer representation of it. And we will add here optional. Or implement you can do floats in the string. This function will need to have a different name because it has the same arguments, just a different return type, and at this point we cannot differentiate, make it differentiate automatically, so note. Of so if you would create a wide character version, then you could keep the name of the function. Okay, so that's that, and now let's continue. So we have seen that we can create specialized versions of our functions. We have created an own complex template type. Now let's take a look into yet another useful thing that we can do with templates. That is, we can use so-called lambda functions in a much more useful way. So as you might remember, when we were talking about function pointers, I mentioned that you can have such a thing like a lambda function. So basically a function which is defined inside of your of any other function as which can be used. So to we'll quickly remember. So let's quickly try this. My add. It's called my add. And then we can use the function like any other function pointer. So and more or less this is not different than having assigned here a function which would have defined there, which would do the same thing. So we can quickly just for demonstration int my add, better reduce than my add func. So functionally this line and that line would be identical. Would be identical, just that the function lives somewhere else. So this function here is really explicitly placed outside, while this function is here, and the compiler might opt to actually keep it in there, or it will move it out and put it somewhere. But what we see here generally is that we are limited in as far as for now we will only be able to kind of use functions which have a simple type. And what we can do also with lambda functions is we can create a so-called captcha list. So in this example we don't have any additional data. The function only does whatever it is here implemented internally. It has no access to variables other than global variables or the arguments passed to it. But obviously this is not always satisfactory. So if you know JavaScript, for example, then you would have noticed that there very often you have functions within functions which then access variables from the scope of the parent function and do any sort of crazy things. And obviously the makers or the developers of C++ thought that that's kind of dangerous but also kind of useful, so they thought of a way of enabling such functionality with C++ lambda functions. So let's give an example of that. So let's say int var c is equals answer die, was equals, I don't know, 100, let's go for 100. And now of course here, as mentioned, as is, we cannot use the outside variable, so maybe use a non-capital C. But what we can do is we can specify the variable here in a captcha list, and then we can use it. And if we specify it like this, then we will get a copy of the variable. If we specify it like this, then we'll get a reference on the variable. So a variable specified this way, we could even modify it if we would want to. And we can also just specify just reference, which will give us access to the entire scope of whatever the parent function has access to. So if the parent function would be a part of some class, then we could even in principle access any member of that class. The problem here with such functions we will see in a minute. So let's before we do that, let's quickly comment it out. Implement again the simple harmless version, and let's create a function which will use our other functions. So int call, we just call it with double L, int call lambda, and it will take int asterisk func int, and here we can just return func. Alright, and we want the argument, so int a, int b, func a comma b. So obviously it's a very simple example. but there are good use cases where you would use this mechanism. So for example, if you would have some function that allows you to sort some more abstract object, and you want to enforce some own sorting rules, then for example you would call the sort function and pass to it as argument another function which takes two values of a given type and then returns an information whether they are equals or which one of the passed arguments is larger than the other. So this, for example, would be a very concrete use case for such a mechanism. Another concrete use case would be if you would have any sort of callback. So basically, a common example from the Windows realm would be there is a function called enumWindow, which takes a handle to a callback function and then calls this callback function, providing to it the window ID of every window on the desktop, such that you can iterate through all the open windows that there are. The reasons why such callback functions are used amongst many is that so that two main scenarios where they are used. One is when you'd want to register a callback with something which runs asynchronously and then will from time to time invoke this function. This is the more hardcore use case, so to say. And the other use case is if you are, for example, iterating through something, enumerating something, and instead of having to create a list which you then of results which you then return, which might require a lot of memory allocation, instead you just call a function and iterate through whichever internal list you already have, and just then give the function the different pointers for your internal objects. So and of course there are much more other use cases, but these are like the two most popular from the top of my head. So let's do it. So instead of calling the function directly, here we will use our call lambda. Oops. Call lambda, comma, and sorry, my add, and then we more or less do it like this, and it works, and the result will work. So I think the result is 3. That's an old sample. So as you see, it does what we expect it to do. But now if we try to use the other lambda function, the one with the capture list, so let's go with var_c, then we see that here now our call lambda is no longer happy. It doesn't want to take this now differently typed function. You can take a look on how the error looks exactly. As you see, it's kind of a long error message which more or less just indicates that this is not a type which our call lambda can handle. So what we can do now is we can turn this function into a template. So we can grab some template t instead of typing it, and then we use template t func instead, and now our call lambda can now really nicely execute and will work. Of course the result is different because we have added here this 100 thing. If we go to decimal view, we see that what we wanted it to do. And this mechanism of using templates to call complex template functions enables you to create much more sophisticated complex mechanisms. So for example, here our my handle, which now the way it was until, well, since we gave it already a template, it can already do this. But if we would have created this handle function and just here give it some more generic function that just takes a void and then does something, then we couldn't do it. But here we could put some other object which is managing our resources into it for us. So if we want a concrete use case, we can obviously implement it. So here let's comment this out. Can't see. Now let's go with the more complex example. As you remember, we had this create heap function. What was it? I don't remember what was it. It should be create heap. No, it was alloc heap. heap alloc, and heap alloc allocates from a heap. We need that. Was that create heap? Let's quickly review our previous source code memory. We had this Windows function that allows us to create our own heap that operates heap create. Great. So close, it's still so far, and the return type is handle. So handle my heap is create heap 000. Right. So we already have copied this, and of course to allocate something is quite easy. We oops, int asterisk heap alloc my heap 0 size int 10. But now to free it, we would need heap free, and this thing needs the heap variable. So what we need to do is now we need to capture heap in our capture list, so that we can access it, and then we can flex as 0, and then of course lpmem is our pointer. And at this point you might already see one problem: we are not deallocating heap anywhere. So we'll need to do this as well, and for this we can use another heap handle. So heap handle takes a create heap, and its cleanup function can be a simple what was it? We don't need that. Destroy heap h. Okay, so we have here our heap handle. So here in principle we don't need this one. We could then use heap semicolon is missing. Of course here pass heap handle as well as that might not work. We will need to check what sort of assignment this will use here, because I think it will want a the assignment operator to be implemented. So for now let's create a dummy variable handle which we reuse here instead. So this will be reference. This will need to be a reference, and then we can use the reference operator we have defined on this for that. Okay, so this should work, and the objects should be destroyed in the reverse order in which they were created. So first the thing should here call this, and then should call that, and this way all the data will be deallocated properly. Let's okay, it's complaining with something. Okay, then let's just doesn't like that. The thing is that this gives us a void back, so we need to adjust this again slightly to do what we wanted to do. Okay, so let's say that we will say that this will be of type void. That will not work either. Because this expects a pointer and it gets this, so this should actually we need to this is annoying. Let's give it a t reference data, which returns MPTR. We can use here data, and then that should be fine. Is there some issue? Yeah, it doesn't like this would need to be a bit more complicated to work ideally. So let's say that's a pair void Stern. And then here this line will complain, but this is easier to fix. To specify the time. What is so we have type one asterisk too much. Is it type pivot, and then it that should be right, pivot asterisk. That is more complicated than expected. So let's say we will specify explicitly we want this to keep a type of void asterisk, and then we need here this to be type def. Let's call it void. Is this void? No, that should be fine. Void should be fine. Then void asterisk heaptel as type name, and then here handle handle. So this will be our deleter. So this is the thing we pass to here. Then we just need to cast this to void Stern. Pivot, I mean. Stern, let's see. Still didn't like it. Create this here directly. Why would it want a default constructor that should not require it? We are passing the right types to it. Okay, let's for simplicity do it line by line. So we have our so that was del. Okay, and here this thing takes handle, but this is not quite right. So this should take void asterisk asterisk, or we could also make it different. We could use int ptr. Yeah, that's the most idiot-proof thing we can do. Let's go with that. Handle. So the type, well, the type would be a ptr asterisk in the end. So this would need a asterisk here, heap delete, and this will be casted to this. That still doesn't work. There's an asterisk missing. Oops. Why doesn't it like that? It should. There is some use case where it creates internally a function which does not take arguments, and then it does not like our let's see whether we are we are fixing the wrong line. So as you see here, while it points you inside the template, it's quite often helpful to take a look on the whole arrow, because in the additional lines it tells you from where the arrow was actually coming from, and in this case it was from here, so it did not like our other lambda function. Question is why I didn't like it. Mistakes int asterisk, it should be the right type. No, and it takes my heap. Then it should. This will not change anything. I think this will still complain that it cannot assign it. With our type, but it doesn't like. It fails during this assignment here, I think, or not. I think I know how to fix that. If we move this into the initializing list, then it should be fine. Yeah. So the problem was, it was a very subtle issue, namely that it wanted to kind of create a empty, unused version of this, and then assign it, and there is no constructor for lambda functions defined. So we need to necessarily use this initialization list instead to skip the process of creating a empty variable mdelete type, and then it works as expected. So let's quickly see if we can simplify this thing here as well. So right, so this we can leave for now. Delete we should be able to put in here as well. The next annoying thing about templates is that they are creating errors usually for the first encounter, and if you would like to have multiple errors in your code, then if you here we had the same issue, but we fixed the issue, and then once it was fixed, it still threw the same error just for the next instance, which where a similar type of issue was encountered. So this simply is just a little bit not so user friendly sometimes. Okay, so let's take the heap here, and from handle punct data. Alright, but we need the heap also here for the other things, so we wanted to extract this again from our data. Okay, we need to cast this to handle. Right, and actually we should see if we, because this should work fine. And I thought, doesn't like the this function here. Let's do it one step at a time. So first let's run this again so I see it works. And right, we wanted to do breakpoints, so just that we see that everything happens in the right order. As you see, first we get the inner, then the outer object gets removed. And now if we want to improve on this, let's do that quickly step by step. So one thing that probably should work is if we change this to just handle. That should maybe be fine. Let's see. No, it doesn't like it. This would need a bit more playing around to make it really nice, because some of the we probably should just use t instead of the asterisk, but then we have the problem with this operator that we cannot implement it this way, since you would need to somehow get the type that the thing is pointing to. So for now we will just leave this as is. What we can do is we can try using this variable instead in our captcha list. Punkt. It doesn't allow us. We need to define data as const t. Then it will allow us to use that. Punkt data. Just that my worry is that it will here perhaps try to make a copy of the object, so it might lead to an issue. Let's try it out. Yeah, it doesn't want to return this const. Okay, so first we do the yeah, and it doesn't do what we want. So at some point it creates a copy, which is then destroyed, and at this point it triggers here already the delete. So as mentioned, our smart pointer is not smart enough to handle the use case where a copy of the object is created. You can see if we do it by reference, then it might not try that. Yeah, that worked fine. So we can pass it by reference, and then it will still run into an error. Why did it do it? Yeah, writing an own smart pointer is just simply put a bit more work. So ideally we would want to make a smart pointer that can handle copying and everything. If you are interested in that, we can try to do it. I want to see where it right, this is reference. Alright, and this we undid. Why is it failing? So it somehow does not handle this reference nicely. That's the other problem. Okay, so let's change data to work like this. Just returns ptr. That should be better. Okay, then it should work fine. Okay. Now it's working correctly. So we had a small mistake with the pointers here. Ideally returning, so I could call it ptr to make it more clear what it is returning. Ptr, and then this works correctly. After this being cast to a handle, and it doesn't need a copy if we pass this here as reference. So then it works with our limited version. So we don't in principle need the heap anymore. So we could here implement it like this. Let's run. Okay, it didn't crash. We should again put breakpoints just to see that everything is executed properly, but as we see here, that is already working much better. One problem is of course that we are still using the uint as a type here, which is not the most convenient thing, but for now we will leave this as is, and can continue to the next part about C++. If you want, we can implement a more complex smart pointer later during the lecture, one which would be able to handle the copy and assignment cases properly. Here, since we don't do it, what we should do is we should ensure that those special cases cannot be triggered. So what we'll do is we'll add a constructor which takes a const reference other and a what was it, reference is equals this notation indicates that these functions cannot be used. So if we would now try to pass this here by value, which would require a copy operation, instead of getting a crash, we should get a proper exception that this is actually that the assignment operator is not accessible, as we are getting now. So it's important if you are creating some own objects for which you know that an assignment or any sort of duplication would lead to a inconsistent state, memory corruption, something you don't want, then that you should create such dummy functions for the copy constructor and for the assignment operator, such that the compiler will not try to create its own versions, which would then operate in a way that would break the principles by which you have set up your existing object. Okay, so I think that is all to templates, at least for the simple things about templates. There are a few more complicated things one can do with templates, but I think this would exceed the scope of a short introduction into templates and their usage. Are there any questions? No questions? Okay, then let's create another project and let's take a look again into exceptions. As you might remember from our one of our previous lectures, we have taken a look on exceptions in just C, but as I mentioned back then, there is another exception handling mechanism which is available in C++, which is quite different and a bit more intended to be used on an everyday basis for flow control, unlike the other one, which only within a very limited scope is useful for flow control. It's good if you just want to use this leave statement and so on, but it's not something that you would want to use on an everyday basis to communicate exceptions to other parts of your application. So in C++, you have similar keywords. Try starts a block which is guarded for exceptions, but we don't need the underscore underscore, it is just try. And to catch an exception we use a different keyword, so there is an except or leaving or something, or final or something, but there is this catch keyword. And if you want catch anything, we use catch with 3 dots, which will catch any C++ exception, but will not give us access to the content of the exception. Okay, so let's include some stdioh so that we can do print. So f, oops, encountered f, encountered in a known exception. And the way we are throwing exception is quite simple. You can just write throw, and then you can throw any type that C or C++ supports. So for example, you could throw just an integer type, so throw 1. If you run it, of course, we will then go into encountered an exception. And if we would want to catch this exception, so let's say we will throw here no, if you want to catch exactly this exception, that's what I want to say, then you can write catch, then you provide the type which you are catching, say in this case int error, so it's an integer error, and then encountered an int error. So if we now run the code, we will see that we encountered an integer exception and we get access to its contents, so we could print it to the screen. If we would instead throw something else, like 0.456, like a floating point, then we will again end up in our unknown exception handler. And in principle, we could of course split this up, so we could have like another try, and then this in this catch in a separate catch block. So that would work as well. So this try and catch mechanism works on multiple levels, and it's important to note that these levels work across function boundaries. So we could have a function void myfunc that would implement this part, and then you would call this function from here, and then everything would still work. So as you see, exceptions are a good way to communicate error states across multiple levels of function calls. So of course we could have a function myfunction2 which calls my function, which calls another function, and so on. And on each level we can act on an exception, or if we don't want to do it or don't know how to, we can delegate this to the next level. So what we also of course could do is we could so we can handle an exception here in our error count 1, 2, 3, and then we can throw it again such that the next level of exception handling will handle it. Of course in this case it says it's an unknown exception because we didn't have another int handler. And what we also of course can do is we can use so if we, for example, could use a string. So strings are quite useful because they allow you to communicate a lot of information about what happened. So we could throw error 1, 2, 3 blah blah, and then we just need to catch it somewhere. Let's say we want to catch it here. It was being const char asterisk error encountered %s comma zack, and in this case we see here that this works as well. Is this clear at this point, or do you want some more examples? Okay, so if this is clear, then I can show you just maybe a few more simple mechanisms. So as you remember here, when we had the integer exception and I wanted to throw it again, and then we used throw and an exception. So we could of course throw something else. We could, for example, throw -1, or what we also could do, well, first of all we should add here \n to make this more pretty, but we could also throw a string. So now we have our first catch and then the other catch, and then if we want to throw the same thing, we could also just write throw, and then it will throw whatever exception we had. So in this case we have an integer exception, and then we again go into this catch all handler which handles everything. But now what we can do is we can add here a int exception handler. Then if we run it, then we'll get, well, the first line from this exception handler and then this line from the second exception handler. So if we want, we can act on exceptions by doing something like printing an error, logging an error, or similar things, and then still let the exception be handled by the upper levels of our exception handling stack. And what we also can do is we can throw a complex data type. So as you might remember, we can use complex data types as arguments for functions or as return arguments, and likewise we can use them here also as errors. So we can create our own exception. Stoked my exception, and we can what could we do? We could give it a string of an arbitrary size, so char stern message, and then maybe some int error code. Then my exception will take a int code and a char stern and a string. Just that, of course, this string, we will want to clean this up, so we will need a destructor for that, which will do delete message, and here we'll make message is equals string and code is equals code. So now what we could do is we can create a new string, char stern my error IMSQ, let's call it my message, new char 100, oops. Then sprintf, we should use the safe version, sprintfs, zack, comma 100, comma or you know what, I have a better idea. Here we will throw the string, the int, and then we'll catch the int, and we will throw a string instead. So let's say error %d, comma int error, and now throw my exception, then we need to provide to it our some error code, let's say error code 1, and the message, my message, and now of course here we will need to create yet another case to catch that. My exception reference my error, that should work, let's see, and printf just %s, comma my error punct message. Okay, let's see if this works as expected. Well, it printed error 123, which seems to be right, so let's say yeah, our error message s, and when we put a breakpoint here, we will see that once it's done with the error handling, it will delete this element, so it will destroy it properly, such that no memory will remain allocated. So as you see, we can use this mechanism for more complex operations. Now what we also could do is, of course, we could throw new, so throw a pointer, which in some cases might also be useful, but then this will not be caught by this, but we will need another catch here, and of course then we need to use this, and then we need of course to delete our error message. So we can put a breakpoint here, just that we see that we arrive at the other position. Do you see? We do, and then we delete it. So this way we can create error objects which can be arbitrarily complex and communicate whatever data we want to communicate to the other parts of our process. As mentioned already with the C exceptions, there is the general limitation that such handling is somewhat compute intensive, so you wouldn't want to write your application such that it throws exceptions all the time as part of normal operation. But if you know that it's unlikely, so in case you have a situation where you can have very often an error of some sort, then you should just use a return type that will just indicate failure of the function and so on. But if you would want to communicate more rare exceptions in a different mechanism, then you can use this exception handling approach. Or if you have a program that generally is expected to work successfully without any errors, then you can also use these exceptions to handle problems that your application might encounter. A typical use case would of course be to check if something didn't happen as expected, then throw an exception. So for example, if you try to open a file which you know that should exist, then and it doesn't, then the open operation would fail, and then you could throw an exception specifying that opening of a file failed, and then as an additional argument specify, for example, which path of the was tried to be opened and which failed, so that if you are then reviewing an error log, then you can find out what happened. Maybe the file, the path was obviously invalid. What you could also do is you can combine errors together. So you could, when the open operation fails, it will allow you to retrieve an error code from the operating system. In case of Windows, you would use get last error for that, and then this error would indicate why the opening operation failed. So if you are just using open, then you only get either success or failure, and in case of success you get the handler, in case of failure you don't, but you don't get from the return value an indication of what went wrong. For that you would need to use this other function that would give you the last error that the Windows API encountered, and with that you would know, okay, the path didn't exist, the file itself didn't exist, the file existed but was logged by another process, so it could not be open, etc. And providing verbose error information usually is quite a good thing, because it helps you to easier find bugs and issues generally with your program. So using a nice complex error structure might be a very nice thing to do. To demonstrate all the things that we have learned here in one, let's say, more concise example, what we can do is let's create a new project. Again, create new project. We'll call it IO samples or IO sample. We will create a project which will open a file and will be able to properly communicate an error if an error is if an error occurs, and then which also would be able to properly clean up the file that was opened with the helper class that we have already created here. So my handle, we will copy this in here because we will be using it. We should here include Windows H. And let's create a function. We will call the function, I will give it the ability to return some error code, so int write file, correct write file. It will take as argument a const char asterisk path, as well as let's say some text to write to the file. It will also be a const char text. The length it will deduce either from the length from the text itself, or we can provide an explicit length. So len, and will by default assign to it -1. So here first, if length is -1, then length is equals string length of text. So if we are using a text which is not a printable ASCII text but some binary data which may contain null characters, then we would need to specify the explicit length. But if we are just using text which is ASCII and not terminated, then here we can get the length using the string length function. Okay. So now let's create now let's first open a file. So use our myhandle file. We should switch this to the C20. Okay, and now can use the create file API. We'll use create file A because we have just a ASCII character. Create file W would be the version for the white character. Desired access will be generic write. Showing mode will be 0, so we don't want to share. We don't want any security descriptors. Create dispositions should be create new. And we can see what this specifies. So as you see, we have a few. So create new will create a new file. Create always will overwrite an existing file with an empty new file if the file already creates. If the file already exists. Open existing would of course open an existing file and fail if the file doesn't. And open always will always succeed, and it will open a file without truncating. So the create new, which we picked for first, will create a file if there is none, but if there is one, then it will fail, and the error it should indicate is that a file with that name already existed. Or of course, if we try to create a file in a folder which doesn't exist, it will throw us a different error. And the two last things to specify is files, flags, and attributes. So file attribute normal. Don't want anything specific, and for the temp file handle we don't want anything, so we just specify a null. And then of course we need here our cleanup. So we have the same problem as we had before, that the template is not optimized to operate with actual handles. It's optimized to work with pointers. Close handle H. And there is another thing we need to check, namely a handle. So if this fails, if create fails, then it will return us not null but a invalid handle value, and we don't want to close that. So if H is equals invalid handle value, then we just return, don't do anything. And just for readability, we can break this into multiple lines, so and we need to close the brackets for that. Okay, we don't need this. Okay, so we have created our file, and now we can check whether it was successful. So if PTR, we call this, then we cast this again to handle. Actually, we can check this without casting. So if this is invalid handle value, then we will throw, and we will of course want to use our own exception class. So let's grab it. I will just slightly improve it here to be more user friendly. We will make it having a max size, so that we don't need to allocate the string ourselves. We'll just then copy it into it. So here will be string copy, destination source code, and default, and we will want to have an option to specify also another error value. So we'll have like an internal error code. So if this happens, then we throw an exception 1 saying couldn't open file. We should provide here the file name, but this would complicate things slightly. Why it's complaining? It must be const. Okay, and then now what we can do, we can use this function from Windows, which will give us the last error which the last Windows API function we called has encountered. The way this works is that for every thread there is a thread environment block in which various status informations about the thread are stored, and one of these fields is this last error value. So Windows API there actually is a function called setLastError which you can use to set this field, but the general idea is that Windows functions are using it to communicate additional error informations. So in this case we will have our own error 1. We can even improve this example and use an enum my errors or my error. No error is 0. File error is 1, and so on. Or file open error. So this is a bit redundant right now, but we can use this enum here. So maybe actually we could use just the path here as the message. So we know it's a file open error, and the message is the path. What would be more complicated is if we would want to create to use printf or something to generate a explicit error message as a string and then package it to our error, because for this we would need to again allocate a string, then use as printf, then copy that string, so it just adds additional steps which we might not want for it to be quick. Generally, actually, this design would be actually a very good practice, because you might want to your error messages to actually be localized. So we would just communicate error numbers, which then you can localize to a string, and then the function would know what message actually contains. So in this case we could actually maybe change message to just data and define our data as being a generic additional information about whatever went wrong, which then our primary error handling function will then format nicely for us. Okay, so we have done this. Then the next thing what we want to do is we want to actually write to a file. So you can use the write file function. It takes a handle. So to get the handle, we need to punct ptr and then we can write something. So let's say that's something we already have. Number of bytes to write, we can write this as well. And then what it wants to do is it wants to return to us how many bytes it has written. So depending on what you are doing, a write operation might not write everything you wanted, and the last one will be null because we are not using this. So obviously if you are writing to a disk, then the operation usually will succeed unless you are kind of running out of disk space. But you can use this write file function to actually write to device objects which do not represent an actual file on disk. So it could be, for example, a network socket or a pipe or just a driver, and that thing might just accept a part of the data that you have provided, and then you would need to kind of wait a short while for the data to be processed internally. For example, on a network socket, for the data to be sent to the other end of your connection, and once it's sent and cleared out of the buffer, you can write again to put new things onto the sent buffer. So in this case you would need to track how many bytes have been sent actually, and then move the offsets of your data to be sent accordingly. But since here we are working with files, we expect this to be except in cases of full disk, always this the value which we have provided. And of course now this can either return true or false, so it can fail. So if it is false, so if it failed, then we will throw another error message. So in this case, with the new error, so let's say error file write error, file write error. We can in this case again provide the path and which error actually occurred, so this remains the same. If we would have additional fields here in our structure, we could, in our exception structure, we could add this information. So what we can do is we can use inheritance. We can use struct my file error, which is derived from my exception. Actually, I should just call it this way, my error, my file exception, since we are using exception, and let's stick to this nomenclature. And this thing will be quite similar, just that it will contain additional information. So my exception, we just invoke the other constructor, code, comma, str, comma, error. Now we have our own part, and what we would want, it would be, for example, word size and size, buffer size and written size. So you can add these two variables here. Although since we always want them, then we need to have them first. Buffer, and since we have the same names, then we can actually initialize them here, because this here the thing is smart enough to. I prefer the W2 here. It is smart enough to know that if it's used as an argument, that it cannot be the same thing. Error is put here, so here we will throw our file exception. He will then add len was the first argument, and bytes written was the second argument. Okay. Alright, so we have written to the file. So the only thing that remains is to close the file, but since here we are using this smart structure, it will close the file for us. So now here, let's try catch reference error, and here we will want to write file. Let's say where do we want to write it to? Repositories, or how do you sample? Let's say we want to write to this directory. We remember that we need to escape all the backslashes, so we do that. Then we give it a test text, and then some text to write. This is a test. Okay, and here, once we are here, so there are two strategies how we can handle it. First one is that we can define another catch for the other type, so that if we have the file type error, well, technically all of those should be file type because this also is a file type. Right, so this is not correct, because then this ones would be 0, so let's don't call this file type error, but my write error, write exception. That is more consistent. Okay. Or IO exception, because when we are reading, we can have the same situation. We want to read a certain length. Let's call it IO exception. We want to read a certain length, and we might only be able to read much less. So this is actually a common case when you are reading a file. If you don't know how large the file is, so don't bother checking how large the file is. So just allocate a large buffer, and then you say to the read file API, read me the whole buffer, and then if the file is bigger than the buffer, then you get your buffer full. If it's less than the buffer, then it will succeed, but the read length will be less than your buffer size. So then you know, at this offset, the data in my buffer are no longer valid, so I only look at the initial portion. So here, let's use this here as a IO exception. And then we can catch both of those things. Obviously triggering this will be difficult since we... No, it won't be. What we can do is we can here ask for permissions to only read the file, and then of course write will fail outright. So actually it's quite easy to trigger. And then inside here what we can have is we can add a switch which will inspect the error code. Case well, there are not so many, we have only an open error. And if we would not have this, so let's for now comment this out. Oops. Then we would have also the other case, write error. We don't handle then why not? Let's handle this case as well. Here we just break, here we also break, but we will print something and then want a default case in case of an exception we don't know. So here we printf, for printf we need stdio again, stdio. Alright, I need to be fast, so print unknown error, %s, comma. So here, as you see, depending on what the error is, we change the string which we failed to write to %s error data. And in this case here, we would just we could add additional information. Or what we also could do here, if we know this type, then we could cast this. But for now, this should be enough. So let's run it. The first expectation, of course, is right, this is unsafe. S, comma, 1, 2, 8. So as you see here, it exited without an error and it created a file test. But now when we run it again, it should fail, and it says failed to open file. Alright, and we did not use the double word error value here. So failed to open file, %s, Abstand, error, Doppelpunkt, %d, Komma, error, Punkt, devo error. And for the write file we should add this as well, so that we know what went wrong. And oops, that is a bug, and let's here add a \n everywhere, so that this lives in our own line. Okay, so let's run again, and we see the error is error 80, which ATL, which means error file exists. There is a WinError-H which defines all the typical Windows error codes which you might encounter. And of course, if we want to trigger a write error, we could comment this line out and make a file where we ask for generic read. And then we need to not create new, but instead open existing. Then when we run it, we will run right. Now we have failed to write file, error 5. Error 5 is access denied. That I don't need to check, that I know by heart. It's a very common error you might encounter. And right, so right, as mentioned, we could do two things. First of all, we can here, if we put this in brackets, we can cast to this. So Stern, it could be a reference. Sorry, tools. And then we could access the additional data we have specified. So comma length %d, comma punct which one we want, buffer size. We don't care for the other one, or length \d/\d. Oh, we just call it size then here, size. Oops, so we have buffer size and punct written size. So if we run this, we will probably get something in 0. Yeah, something in 0. So this works nicely. And of course this here is contingent on the cast actually being successful. If we would throw an exception of which is not of type myIOException, but give it the error code file write error, then we would have a problem. So because then the casting here, since it's a cast that casts everything, it doesn't do any checks, so then it would fail, and we would here try to access invalid memory. So if we don't want this, then we can undo these changes, and instead here use our other mechanism. Right, and of course we still should switch file error, right, and we don't need the brackets. The brackets, the additional brackets inside cases are only needed if you want to define some internal variables. In this case we don't, because the type error already contains the right thingies. So here we will see that if we run it now, the exception dispatch is smart enough to direct us to the specialized case, even though the next one would also be compatible. But if it finds one that is even more compatible, then it uses it. And of course, if we now remove the file, since we chose open existing and we are now kind of trying to read from it, we'll here again fall into this error code 1, which is file open error situation. And there's one more thing which we forgot to test, so let's comment this line out and this line in, is the deletion, the closure of the handle. So if we, let's enable this, okay, so let's go for the breakpoint here. So now, so at this point we already have an error, so you see this the invalid error value, it's all F's, which is -1. At this point it didn't do anything yet. Did this fail? Oh yeah, sure, it failed because here we don't do anything. Let's put the breakpoint at the higher level. Now it will. Okay, so we arrive here, then we let's put breakpoints here and there, make play. So as you see, as soon as the exception was triggered for this code block, already the unwind code is executed, but in this case our function returns early, since it sees that the value has not been set to valid, so it doesn't need to do anything. And only then here we enter our exception dispatch. This is decisively different than the try except mechanism that you know from C, where once your exception initial exception handle is triggered, then you can kind of make decisions, and you could in principle resume the operation. Here you don't have this liberty. Once you end up in an exception handle, the rest of the code already has been unwound, and the only thing remaining is the exception itself. So if we remove those breakpoints and just run it, then we see that here in the call stack we don't have the other function anymore. We only have some internal functions from let's load symbols from the NTDLL and from the C runtime. Load symbols. Yeah. So that's that. So as you see, the different abilities of C++ to track this variable scope and the proper usage of your own data types allows you to not need to manually manage your resources. You can set your code up such that no matter what happens, it will always release resources when needed. During one of the later lectures we will actually implement a much more flexible smart pointer implementation, one which allows us to have reference counting, so that you can have a variable which is a smart pointer to which you can assign another smart pointer, and then you can do something with that, and then you can destroy these variables in an arbitrary order, and as soon as you destroy the last variable, then and only then the memory which the variable points to will be freed and released. So with that we will have pretty much full custom memory management, allowing us to write quite safe C++ code. Now it's almost 17 o'clock, so as it probably was sent to you by email already, there will be a evaluation of the lecture today. So I think you have got some links on which you can click to start the evaluation. So I would ask you to do it, since it's supposed to be done in present, so it's not like homework or something you can do later, but it needs to be done during the lecture. I don't remember how much time you might need for it, just I would say let me know when you are done. I think half an hour should be more than enough. If we have time left, then we will continue with something interesting. We could take a look on something that will be subject during the next lecture, which will be the various STL types, which pretty much implement all the useful things like smart pointers and so on for us. And if we don't have any time left, then we just quit early, since we are supposed to have like 15 minutes breaks, which I usually forget to do. If you need like more than 15 minutes for the evaluation questionnaire, then we can finish at 17:15 for today, as you prefer. So just please write in the chat if you have got the email and if you got some link and if this works for you, so that I know that everything is fine. And I will stop the recording for now.